In this lecture segment, we'll look at how negative values are represented in binary in a signed integer type variable. If you're already familiar with 2's complement notation, you may find some of this review, but you may also get a new perspective on the concept. Many people are taught 2's complement in a rather rote way, but we'll be looking closely at the intuitive rationale for the notation. Before we discuss 2's complement, let's first do an overview of what it looks like to count in binary from 0 to 65,535 in a 2-byte unsigned integer. Lines 4 through 21 outline the pattern, and I've used ellipses to keep it from being 800 pages long. Of note for our conversation are the values 32,767 and 32,768, straddling the halfway mark. 32,767 is the highest value that still has a 0 for the most significant bit, the MSB, which bit has place value 32,768. A side note on bit numbering, by the way, the MSB has value 2 to the 15th power despite being the 16th bit, since the least significant bit, or LSB, has place value 1, which is 2 to the 0, not 2 to the 1. Indeed, in order to number bit positions according to the power of 2 they represent, it's common practice to number them from right to left, with bit 0 in the LSB position up to bit 15 in the MSB. And to be sure you see how the bit patterns in the highest several values work, culminating with the all ones pattern of 65,535. And we'll get to those negative values over here, by the way, in a moment. For instance, it should be clear that 65,533, say, has a 0 in the 2's place, since it is 2 less than 65,535. So question 1, on that basis, without using a calculator or anything other than your memorized powers of 2, write down the bit pattern for 65,502. That should be doable in under 30 seconds, and should not require counting backward in base 2 either. Think in terms of the difference between 65,535 and 65,502, and what that means in terms of 0 bits that you should insert. So, coming back from a pause there, (65,502) has bit pattern all ones, but with zeros there. And I'll leave a gap between the bytes for readability. That's 65,535 with the 32's place and the 1's place knocked out, or set to 0, to reduce its value by 33, thus arriving at 65,502. The point here is to get you reasoning backwards from the highest value of 65,535 with the 0 bits indicating how much you subtracted from 65,535. If that's obvious by now, great. But if it took you more than a few seconds to do question 1, here's another set to practice with. Give bit patterns, please, for 65,519, 65,518, and 65,517. Coming back from a pause there, these values are 16, 17, and 18 less than 65,535, respectively. So the bit pattern for 65,519, 16 less, is that with the 16's place zeroed out, and of course 65,518 that with the 16's and 1's place zeroed out, and finally 65,517 with the 16 and 2's places zeroed out. Thus. And note something about those values which will be important as we look at 2's complement notation. As we descend in value, the 0-bit patterns are counting upward in binary, since they show what we are subtracting from 65,535. Now, what happens if we add 1 to 65,535? In typical binary counting fashion, all the 1's flip back to 0. If there were a 17th bit, a bit 16 given our numbering system, right, it would go to 1, and we'd have 1 followed by 16 zeros, or 65,536. But there is no bit 16. So that final carry at the top has no effect, and we're left with just the zeros. This is the way binary addition hardware works on almost every computer. When you add 1 to the highest value, it wraps back to 0. There's a familiar example of this phenomenon in base 10 form. Anyone who drives a car knows that the typical odometer, the counter that registers miles driven, goes up to 99,999, and then it flips back to all zeros. And those students in advanced nations, by the way, that use metric units may be more familiar with 6-digit odometers that read in kilometers. Please excuse the U.S. bias here. The idea is the same either way. So after 100,000 miles, you get a brand new car starting at 0. Too bad the new car smell doesn't come along with that. Now, I'd like to suggest a different view of that 99,999 odometer figure. I suggest that instead of a high mileage, it signifies actually a low mileage. In fact, a mileage of -1. This seems reasonable because adding 1 to it produces 0. And of course, I'd suggest that 99,998 is in fact -2, since adding 2 to it produces 0. It's not an old car, it just has a few miles to go before it's brand new. So, does this really work, or is it merely a game? Well, for instance, what would happen if I started with 100 on my odometer, and then I drove 99,998 miles, which I'm interpreting as -2 miles? What would the odometer read after that? And is that consistent with interpreting 99998 as -2? Stop and think about that for a minute. For an answer there, if you think about it, the odometer would read 98 after this. We'd wrap all the way back to 0 and make it almost all the way back to 100, less 2 miles. In this case, 99998 works, just like a -2. This is a general pattern. You can try it out with different examples. 99,998 can be viewed as -2, mathematically, on an odometer. Any mechanical system that adds on an odometer-like meter will work without modification if we take that view. Okay, so just how far do we carry this? Is 99,900 actually -100 then? Is 60,000 actually -40,000? Heck, is just 1,000 actually -99,000? It's really a matter of convention, and the standard rule in 10's complement, which is the name for this concept, is that any value halfway up the range or higher, i.e. 50,000 or higher, is viewed as negative, and those less are viewed as positive. Now, we have all the pieces in place to discuss 2's complement. The concept is the same as the 10's complement idea just discussed. Repurpose the top half of the unsigned range to serve as negative values, taking advantage of the fact that cyclic arithmetic makes them act just like negative values. The only difference is that we work in base 2. So, looking again at lines 4 through 21, we see that we can view the values from 32,768 to 65,535, which is the analog of 50,099 in our odometer example. We can view those as negative. Thus, an all 1's value is not 65,535, but -1. 65,534 is -2, and so on. And the point at which we break from positive to negative, the halfway point of the range, is where the MSB turns to 1. 32,767 is still positive, but 32,768 becomes minus 32,768. All values with MSB 1 are considered negative, and the MSB is sometimes called the sign bit for this reason. And importantly, any hardware, like a CPU add circuit, that works on unsigned values works just as well on 2's complement signed values, since the cyclic wraparound at 0 naturally lets us treat high positive values as though they were less than 0. This is why 2's complement is so universal. It takes virtually no hardware changes to implement it, just a point of view change regarding the meaning of the top half of the number range. It is now easy to see why integer overflow works as it does. In the unsigned case, the overflow is from 65,535 back to 0. But in the signed case, the jump is from 0 and all ones, or 32,767, to 1 and all zeros, or negative 32,768. So overflow in the signed case occurs halfway up the unsigned range and jumps from the highest positive value back to the lowest negative one. One way we might choose to represent negative numbers is to designate the MSB as a sign bit. 1 means negative and 0 means positive, and then just have the rest of the bits give the absolute value of the number. Now, is this the same thing as 2's complement? If so, explain how, and if not, give at least one example of a number that would be represented differently under the sign bit and absolute value scheme I just described than under 2's complement. Again, the scheme here is use a sign bit followed by the absolute value of the number in question. So, coming back from that pause, they're not the same. For instance, in the sign bit scheme, minus 1 would be 1 for the sign bit, followed by all zeros and a 1 in the ones position. But under 2's complement, of course, it's all ones, period. The formal name for the sign bit concept just discussed is sign magnitude representation, and it is actually used in parts of floating point notation, but not in integer representation on most machines, because the hardware to do it is more complex. Question 5. Translate the 2's complement concept into a 1-byte signed character. What bit pattern is the lowest negative number in that case, and what value does it represent? What bit pattern and value are the highest positive number? Again, in a signed char. Coming back from a pause, the bit pattern 1 followed by 7 zeros, or negative 128, is the lowest negative. A 0 followed by 7 ones, or 127, is the highest positive. And by the way, the same reasoning for a signed 4-byte integer gives you a lowest value of negative 2 to the 31st power, or negative 2,147,483,648, and the highest value is positive 2 to the 31st less 1, the same number in positive form, but 647 instead of 48. Now that we have the conceptual view of 2's complement, there's a convenient trick for converting from the bit pattern for a positive value to the 2's complement pattern for its corresponding negative value, converting from 3 to minus 3, for instance. It's based on the earlier observation that if we look at the 0 bits in the negative values, they represent how much was subtracted from the all ones value, from 65,535 in our 16-bit case, and thus they count upward in binary as we go downward in value. Look at lines 20 through 17, for instance, in that order to reinforce this. The 0 bits in the values from 65,534 down to 65,531 count from 1 upward to 4 in binary as we descend, since they represent how much we're subtracting from 65,535. So here's question 6. This suggests that if we just flip the bits in the negative values, changing ones to zeros and vice versa, we'll get the corresponding positive value. Is that so? Try it out on an example or two. Coming back from a pause, again in which I hope you tried it out, you'll find that no, it's not quite true. The bits for minus 2, for instance, flip into the bits for positive 1, and those for minus 3 flip into the bits for positive 2, etc. And of course, the bits for minus 1 flip into the bits for 0, not for positive 1. So we do need a small adjustment. We can get the right result by flipping the bits and then adding 1. So then the bits for minus 2, for instance, convert to those for plus 2. They convert by flipping to 1, and 1 more makes 2. It works in the other direction too, by the way. The bits for plus 2 here flip into those for minus 3, but then adding 1 adjusts to the value minus 2. So we arrive at this mathematical trick. In 2's complement, to convert from negative to positive, or vice versa, flip all the bits and add 1. Remarkably, this little trick is sometimes used as the definition of 2's complement, perhaps because it's easy to state. But it misses the entire intuitive reason for 2's complement notation, which is far more important. Think of 2's complement as redefining half the range of values to be negative, relying on wrapping back to 0 to make that work without special hardware. That's what it's really about. This flip the bits and add 1 is just a math trick to let you do negation in 2's complement easily. A bit of external research for you. There are several ways to represent negative values. 2's complement is just by far the most common. We've seen sign magnitude earlier in this segment. Do some external research on 1's complement notation and answer this question. What is the representation for negative 1 in 1's complement? Assume 16 bits. And what odd thing occurs regarding the value of 0 in 1's complement? Coming back from a pause there. Minus 1 is what would be minus 2 in 2's complement. 1, 1, 1, 1, and a 0 at the end. And it's the result of directly bit flipping plus 1, which is how 1's complement produces negative values, by a simple bit flip. The odd thing about 0 in this case is that there are two ways to represent it in 1's complement, all zeros or all ones. In effect, one gets a positive 0 and a negative 0. Rather odd, which perhaps explains why you don't see 1's complement used much these days. And a second research question. Look up how fractional values are represented with bits to the right of the binary point. The Review C lectures cover this in the Data Representation segment, so look that up. Reminding yourself how this works may be useful in the LMQs, fair warning, and will be useful in question 8 here. What is the binary representation, first, of decimal 2.5? How do you write that in binary? How about 3.75 or 5.375? And once you've got those, extend your reasoning a bit to ask, what would be the binary representation under 2's complement for negative 1.75? So coming back from a pause there, first the positive values. If you want to do a decimal 2.5, then what you need to do is write in binary 10 for 2.1. From your review of the numerical representation systems, of fractional binary systems, you know that the place value right after the decimal point, or binary point as it should be called, is 1/2. So that's a 2.5. And carrying that a bit further, if you want to do 3.75, then you need to write 3 and a 1/2 and a 1/4. And the place value after 1/2 is 1/4, descending by powers of 2, of course, in the fractional direction. If you wanted 5.375, you'd get 5 and no half, 1/4, and 1/8. Now, minus 1.75. The key insight here is if you're thinking in 2's complement, that should be a value such that, in 16 bits anyway, plus the fractional part, if we add 1.75 to it, we'll get back to 0. And that would be minus 2 plus another 1/4. Sorry, there. And in 2's complement notation, that if you add 1.75 to it, will come back to all zeros.